Hello, my beautiful computer science students. Welcome to Unit 10 Recursion, where we are going to go through the first lesson of this unit, which is an introduction into what recursion is and what it looks like. So I'm excited to dive in. This is one of my favorite units and favorite topics is recursion. So let's talk about what it is. And I want to talk about what it is by introducing something you've seen before in your math classes. And we're going to tie it into recursion here. So I want you to recall piecewise functions, and maybe it's a topic you haven't had to think about for a while, but we're going to think about it today. So if you try to think back and remember, you've covered this, you usually cover it in an Algebra 2 class, maybe Algebra 1, but you've covered it in your algebra classes. And a piecewise function is a function that has pieces, and which piece you use depends on what your domain is, right? So I have my piecewise function off to the left there, f of x equals, and then it equals two things, either 2 times x minus 1, or it equals 3. Now, which one do I evaluate? Well, it depends on what x is, right? If x is greater than 1, I'm going to use this function. If x is less than or equal to 1, I'm going to use this function. So when I evaluate, like if I want f of 0, 0 is my x, and I pick which one to evaluate based on which range x falls in, right? So 0 is less than 1, which means f of 0 is going to be equal to 3. Okay. So coming back to piecewise functions, okay. Let's evaluate f of 1 now. So f of 1 is less than or equal to 1. So f of 1 is also going to be 3. Once we reach f of 2, 2 as my x value is greater than 1. So I use the top piece of my piecewise because 2 is greater than 1. So I substitute 2 into this equation for x, and I get 2 times 2 minus 1, which evaluates to 2, right? Because 2 minus 1 is 1, 2 times 1 is 2. Same thing with 3, okay? 3 is bigger than 1, so I use the top piece. 2 times 3 minus 1 evaluates to 4, okay? So a recap of piecewise functions, real quick. Now, we can actually make a method of this. So we're going to write the code that codes this piecewise function. So technically it's a static method, but I couldn't fit the word static in there. This method is called f, and it takes an input x, and it's going to put out an integer. Okay, exactly like what we did here. We have an input and then we have an output, and we're going to code that piecewise. Now, how do we code a piecewise? Well, the piecewise asks a question first. Is x greater than 1, or is x less than or equal to 1? And you evaluate based on the answer to that question. And how do we ask questions in Java? With an if statement, or in this case, an if-else statement, right? So we have two options. Is x greater than 1? Else x would be less than or equal to 1, right? So this if-else statement covers all values of x, okay? So we ask the question, if x is greater than 1, then I want the integer that is returned to be evaluated like this. Else, I want it to be evaluated like this. And that just looks like a simple return statement. So you would return 2 times x minus 1, okay, taking that value of x, subtracting 1, and then multiplying by 2. Else you return just a 3. Okay. So this is all kind of review here. We're reviewing piecewise, and we're kind of showing how we can fit a piecewise function into a Java method. Okay. We have no recursion right now. No recursion. But we will in the next problem. Okay, let's look at a different piecewise function. This is a piecewise function that is a composite function. And you've had composite functions before. I promise you have. In Algebra 2 is when you go over composite functions. But you've had them before. And composite functions are an example of recursion. Very exciting. So let me convince you that it's an example of recursion. So here I have a new function, g of x, and notice it's the same as the piecewise that we just got through, except I have this right here. Okay, 2 times g of x minus 1. Okay? So I have a function inside of a function. In your algebra classes, that tends to look like this, right? A function inside of a function. Okay? Let's go over how we evaluate those again before we get to the Java code. So like g of 0, okay? 0 is less than or equal to 1, so it's just a 3, right? Same thing with a 1. 1 is less than or equal to 1, so it's going to evaluate to 3. Okay? Now let's get into g of 2, right? 2 is greater than 1, so I'm going to evaluate this using this. Now, oops, I kind of crossed it off. So how do I evaluate that? Well, I still substitute in the 2 for the x value. Okay, so I get 2 times g 2 minus 1. Okay? And 2 minus 1 is just a 1, so I put that there. Okay, so now how do I evaluate this? Well, this g of 1 has already been evaluated, right? It was evaluated right here. G of 1 is equal to 3. Okay? So because you know what g of 1 is, you know that that output, if you plug in 1 to g, you know that that output is 3. So you make that substitution. This becomes 3, because you already solved what g of 1 was equal to, okay, kind of like a substitution. And then you take 2 times 3, which is 6. So g of 2 is equal to 6. So these composite functions and this composite piecewise, when you evaluate a function, sometimes you have to look at what another function evaluated to. Okay, like in order to solve g of 2, you had to know what g of 1 evaluated to. And we already found out what g of 1 evaluated to. Okay, here's another example, g of 3. 3 is greater than 1, so I'm going to do the same thing right here. I'm going to plug the 3 in for x right here. 3 minus 1 is 2. So I have 2 times g of 2. Okay. So in order to find what g of 3 is, I have to know what g of 2 is. Okay. So what was g of 2? I just solved it right up here. Okay. I know that g of 2 is equal to 6. So I make that substitution. 2 times 6 is 12. So g of 3 is 12. Yeah. Composite functions, specifically a composite piecewise function. Very exciting, but how can we make this into a method? Well, that's where recursion comes in. And it's just a small little thing that slips into the method that makes it recursive. It's going to look very similar to what we just wrote above. For example, we first have to ask a question. Is x greater than 1 or is x less than or equal to 1? And that is still accomplished with that if statement, okay? That if-else statement. So if x is greater than 1, we want to evaluate this. If x is less than or equal to 1, we want to evaluate this. Okay? And we want to return it, right? We want to return this. So what do? Well, we write it, right? 2 times g of x minus 1. Or we return 3. Okay. Now this right here, okay, this is the new piece. This is the recursive piece because I'm making a method call right here. This g is not a variable, right? G is my method. Okay, G is my method. So when I have this right here, this is a method call. So the method calls on itself. Calls on itself and it says, hey self, I need you to evaluate this for 1 less than the x value I'm currently at. All right? That's your recursive method. And that's all it takes to make a method recursive. It's very exciting. Okay? Now how we would trace this, we're going to talk about in this lesson. Okay? We're going to talk about how we actually go through and evaluate what is returned in something like this. Okay? But now that we've seen recursion, let's define it a little bit more with some words. Okay? A method that calls itself, that's a recursive method. That's what it takes to make a method recursive, is it has to call on itself. So here, the fact that I added g and it called on itself, that's what makes g a recursive method. If it calls on a different method, it's not recursive. It has to call on itself to be recursive. The recursive call is when a method calls on itself to execute. Okay? So a recursive call happens when it has that self method call, when it calls on itself. The reason we have recursion and the reason we can use recursion in Java is it's actually easier to code, and it results in like what we say a prettier or more elegant solution a lot of the times than something that wouldn't use recursion. Okay. The disadvantages is it usually takes more memory and it tends to be slower. If you're using Replit, you'll notice that recursion goes a lot slower on Replit. If you're using like BlueJ or Eclipse, more of a programmed IDE, those tend to go a little bit quicker. You might not notice a difference with recursive solutions versus iterative solutions, but generally a recursive solution does take a little bit longer. Because it's calling on itself multiple times, and each time it calls on itself, it has to store the local variables. Okay? And we'll get into talking about what that means when we see examples of tracing through, and exactly what do we have to keep track of when we're trying to evaluate a recursive method. Okay? So advantages, it looks easier. Disadvantages is it is a little bit slower. Okay? It is a little bit slower. So evaluating a recursive function, the steps we are going to take to evaluate a recursive function. There's technically two techniques. There's bottom down bottom up and top down. The bottom up technique is what we did with piecewise functions, where we evaluated what we call a base case. So we evaluated the lower values of x, and then we kept increasing x until we got to the problem we wanted solved, right? We evaluated g of 0, g of 1, g of 2, and then we evaluated up to g of 3, up to g of 3. So that's your bottom up, if I get that correct. The top down is what we are going to focus on. So I really like the top-down technique when we're evaluating recursive functions by hand. I just think it's a little bit easier to do the top-down technique, and it just seems a bit more intuitive. So here are the steps we're going to use to evaluate this. So first we start with the larger problem. So we're going to begin with some problem we want to evaluate, right? Whatever the problem gives us, we want to evaluate it. And we're going to break that problem down into smaller sub-problems. So this involves calling the same function or the same method with reduced input parameters, right? Or sometimes increased parameters, but you'll see. But usually smaller input parameters, and we're going to break it down, okay, right? Going from the top, the larger problems, break it down into sub-problems, until we get to what's called the base case, okay? So base cases are the smallest instances of the problem that can be solved directly without further recursion, okay? That's the official definition of a base case, right? So a base case is just basically where the recursion stops, okay? A base case has no other recursive call. It is where we end, okay? And then once we reach the base case, we have to substitute back up the chain to evaluate our larger problem. Okay? We are going to combine all of the solutions we got until we get back up to that larger problem and we have a solution that we solved for. Okay? So here is a recursive method, and we are going to evaluate it using the top-down technique. Okay? So I want you to look at this. It says, given the following recursive method, evaluate calculate for. Okay, so calculate is the name of the method, and notice in here I have an if-else statement. If a is less than or equal to 0, return 0. Okay, so this right here, this is my base case. Okay, once a is equal or less than 0, I return 0, and I have no more method calls. Otherwise, notice the else statement here. Inside that else statement, I have return a minus calculate a minus 1. So I have a recursive method call in here. Okay? So that's going to be my recursive call. So how I evaluate this, start with the big problem, right? I want to evaluate calculate 4 and go through the method and evaluate it first with a equals 4, right? So 4 is 4 less than or equal to 0? It is not, so I'm going to run this else statement. And in this else statement, a is 4. Okay. So I want to return this. Okay. I return that with 4 substituted in for a. Okay, because on this method call of calculate 4, a is 4. So 4 minus calculate, 4 minus 1 is going to be 3. So that becomes calculate 3. So in order to evaluate calculate 4, I have to first know what calculate 3 is. And then I take 4 minus whatever calculate 3 is, and I get my answer. So I have to now figure out what calculate 3 is. Okay. So now I go through the method with a equals 3. Okay. Is 3 less than or equal to 0? Nope. So I'm going to return this now with a being 3. Okay. So calculate 3 is equal to 3 minus calculate 2, because 3 minus 1 is 2. So now I have to figure out what calculate 2 is. Okay. So 2 is for a. So I substitute in 2 for a. I go through, and calculate 2 returns 2 minus calculate 1. So now I have to figure out what calculate 1 is. I substitute in a equals 1, and I get 1 minus calculate 0. Okay, so you see the pattern that's happening here, right? And usually recursion has some sort of pattern like this. Okay, it looks like an iteration of sorts, right? Some sort of iterative pattern. But you keep on breaking this problem down until you reach the base case. And that's where calculate 0 comes in. Okay? Calculate 0. When a is 0, I have reached my base case. Okay? This is my base case. So calculate 0 returns 0. And I have no more recursive calls. Okay? I've reached my base case. Now I have to substitute back up and evaluate calculate 4. 0 is not my answer. Okay? 0 is just where it stops, right? I have to substitute my values back in. So I have to substitute 0 in for calculate 0. Okay? And that becomes 1 minus 0, which of course is 1. So then I substitute 1 back into calculate 1. 2 minus 1 is 1. So calculate 2 evaluates to 1. Substitute 1 in for calculate 2. 3 minus 1 is 2. So calculate 3 evaluated to 2. Substitute 2 into calculate 3. And then I get 4 minus 2, which evaluates to 2. And I have my answer. Calculate 4 is equal to 2. It evaluates to 2. Okay. Yeah. So tracing through recursion, this is the top down. You start with the larger problem, break it down till you reach that base case, and then substitute back up. Okay. So again, top down, I like it because for me it feels more intuitive and more how we align with problems and problem solving in general, where we take a problem and we break it down into smaller, simpler components. If you are interested in learning the bottom up technique, feel free to Google it, check it out. Again, it's very similar to how we solved those piecewise functions. Bottom up starts with your base case. Now, for this example, it was kind of easy to figure out what our base case was, but I will warn you, not all recursive methods have an easily identifiable base case. And because of those circumstances, sometimes it's not easy to identify the base case. That's why I tend to go with the top-down problem solving more so. Okay. All right. Well, you know what time it is now. Now we are going to practice. Okay. So with any of these, as we go through, I have 4 practice problems. If you wanted to pause and try to work them out on your own first and then press play when you're ready to see the answer, feel free to do that. Otherwise, I'm just going to go through the problem and go through how we would trace through and get our answer. Okay, this first one, it looks very similar to what we just went through. It's called method A int n. If n is equal to 0, you return 0, else you return n plus method A n minus 1. Okay, so we want to evaluate method A5. So going through first to evaluate method A5, n is going to be 5. Okay. Now remember earlier when I talked about how recursion takes longer just because it has so many local variables to keep track of? That's because with the first method call, your local variable is 5. Okay. So I'm just going to call it A of 5, but it's method A. Okay. Just something just to make it a little bit easier to write out, especially if you're tracing it by hand. Sometimes it's hard to write out the entire method name every time. So I'm just going to call it A of 5. Okay. Now, when I first go through, n is 5, right? So because n is not equal to 0, I return 5 plus method A, 5 minus 1, which is 4. So that first time through, my local variable is 5. Okay. Now, with my next recursive call, it says, okay, I can't evaluate A of 5 until I figure out what A of 4 is. So the next time I call my A of 4, my local variable n is going to be 4. Okay. So I return 4 plus A of 3. Okay. So I pause and I have to figure out what A of 3 is. Okay. So what's happening in the program is it's defining these local variables. N is 5, n is 4. Next, we're going to have n is 3. And it has to keep track of all of those as we go through our recursive call. Okay, almost like a method chain in a way, because in order to figure out what this evaluates to, you have to pause it for a second and figure out what this evaluates to. But then you have to pause this and figure out what this piece evaluates to. So it can just take a lot of space in memory keeping track of those variables, right? When n is 3, we return 3 plus A of 2. When A of 2, okay, I still haven't reached my base case. A of 1, still haven't reached my base case. I've reached my base case. A of 0 equals 0. It returns 0, and the recursion stops. Okay. But remember, that's your base case. That's not saying that your answer is 0. Okay. In order to figure out what your answer is, you have to substitute that back in. So 1 plus 0 is 1. Okay. And then 2 plus 1 is 3. 3 plus 3 is 6. 4 plus 6 is 10. And then 5 plus 10 is 15. So you take this and you substitute it back in. Then you take this and you substitute this. Then you take this and you substitute this, right? So it's like a little chain where you substitute all of those back in for those functions, for lack of a better word. So your answer here, method A of 5, okay, with an input of 5, will return 15. Okay, let's look at the next example. Method B. Again, if n equals 0, this time we return 1 is our base case. You can return anything as your base case. It doesn't have to return 0. It can return 1. It can return a random number. You'll see in the next couple lessons it could just be a print statement. It could return a string of some kind, a Boolean. It can return anything. Your base case is whatever you define it as. We're just going to go through some simple examples. So our base case returns 1 in this. Okay, so method B, going through n is going to be 10, okay? So I return 10 times B of 8, because in my recursive call here, now I'm taking n minus 2, okay? You can manipulate your parameter however you would like to, okay? If you want to subtract 1, subtract 2, subtract 10, divide by 10, you know, add 10, whatever you want to do to your parameter in there. Okay. And we go through, right? B of 8 is 8 times B of 6. B of 6 is 6 times B of 4. Again, you'll kind of see a pattern, and you can use that to your advantage and just kind of continue the pattern until you reach your base case, which is, in this case, B of 0. Okay. When n is 0, I return a 1, and I've reached the end. Now I go back and I substitute in. 2 times 1 is 2. 4 times 2 is 8. 6 times 8 is 48. 8 times 48, 384. 10 times 384, 3,840. That one was kind of a big one. Just know if you are taking the AP exam, you're not allowed a calculator on the AP exam, so they usually wouldn't ask you such a big numbered question here. But you can use a calculator for these types of problems. Just know you can't use one on the AP exam. All right, let's look at the next method, method C. This time we're going to take 2 parameters as our input here. So again, this shows you that you can take 2, 3, 4, 5, however many parameters. I've really only seen 1 to 2. Otherwise, it just gets kind of crazy. So we'll stick with that. But for here, we have to keep track of 2 local variables now. And in the if-else statement, you see if b is not equal to 0, then we have a recursive call. And the recursive call takes a plus method C again, and it manipulates both A and B. Okay? Else return A. Okay? So this base case, I can identify the base case as long as B is not equal to 0, this is what I return. So the base case, I return A when B is equal to 0. Okay? So here's what I want to evaluate, method C, 3, 4. Okay? So 3, 4. So 3 is going to be A. 3 is A, and 4 is going to be B. Okay, so because B is not equal to 0, this is the call I'm going to make. So I return 3 plus a recursive call. 3 plus 4, 3. A gets 1 added to it, and B gets 3 subtracted from it. So now I have to figure out what C of 4, 3 is. Okay, so B is not equal to 0, so A is 4, and B is 3. Okay? So then from there, that's going to return 4 plus C of 5, 2. A gets 1 added to it, B gets 2 subtracted from it. Figure it out again. I take A plus C of 6, 1. B is still not 0, so I get 6 plus C of 7, 0. Now I've reached my base case. Because B is equal to 0, I return the value of A. Okay? And then I substitute those back in. 6 plus 7 is 13. 5 plus 13 is 18. 4 plus 18 is 22. And then 3 plus 22 is 25. Okay. So that's a lot of local variables to keep track of as you are going through. So you want to really make sure that you are writing out your trace here. Okay. There might be some easier recursion examples where you might be able to kind of do it in your head. I don't think this is one of them at all. And even if you could probably figure it out in your head, I still highly recommend writing it out. Okay. Keep track of those local variables because you have a lot of them floating around here, right? So that you can get your final answer. Okay, this is going to be our last example here, method D. Again, 2 inputs. It says if A is equal to B, return 0. So that's going to be our base case is when A and B are equal. Else return, and then I have a recursive method call here. Return B plus D. A gets 1 added to it, and B actually stays the same. Okay, so B is going to stay the same. A is going to be the one changing each time. So D of 2, 6 is going to be, excuse me, oh, I have this wrong. Because it returns B plus method D, A plus 1. Okay, so this right here should be B, which is 6. Okay, and I think I did that for all of them as I go through here. Huh, would you look at that? So that's why you got to write it out. Okay, here, so I'll just write this out then. So then I need to figure out D of 3, 6. Okay, so because A and B are not equal, I return the value of B plus D of 4, 6. I add 1 to A. D of 4, 6 is 6 plus D of 5, 6. Still not equal, so I'm still working through. D of 5, 6 is 6 plus d of 6 comma 6. Ooh. Now I've reached my base case call. D of 6 comma 6 is going to return 0. Okay. So now I go back through and I basically add them all up, right? I substitute this in here, substitute everything back in, is adding up all of these values. 6 plus 6 plus 6 plus 6, which is going to be 24 as my answer. Sound good? Another example of why very important to keep track of those base cases. Okay. Now let's move on to our last topic for this lesson, and that's infinite recursion. Okay. So maybe you've kind of been wondering up to this point, maybe you've noticed something about what happens if there's never an end to be reached, right? Here's one example of infinite recursion here. Let's trace through this. It's called mayhem, and it accepts one parameter, okay? So let's say I want to run mayhem 5, right? If I plug 5 in for A, I return mayhem 4. Then I figure out mayhem 4 returns mayhem 3. Mayhem 3 returns mayhem 2. Mayhem 2 returns mayhem 1. When does it end? Well, this wouldn't. Okay, there's no base case, right? It is just a simple return, a recursive call. So this recursion will actually never end, right? And this is our first example of infinite recursion. When there's no base case, you're just continuing to make recursive calls and it never ends, okay? Our second case of infinite recursion, this method is called chaos. I do notice a base case in here. I have a base case defined. When A is equal to 0, I return 0. Okay? So otherwise, I have a recursive call in my else statement. Okay, perfect. So let's run chaos 5. Okay? So chaos 5 is equal to 2 plus chaos 1. Okay? Because I return 2 plus, and then 5 minus 4 is going to be 1. Chaos 1 is equal to 2 plus chaos of -3, because when A is 1, I take 1 minus 4 to get -3. But I could keep going, but I've noticed an issue. If I keep going and I keep subtracting 4 from A, I've all of a sudden skipped my base case. I will never reach my base case. Okay? If you have a base case but it never is reached or it gets skipped somehow in this example, your recursion will never end. Right? And this is the second way you can get infinite recursion, is even if you're careful and you planned a base case, it just never executed. Right? So 2 examples of infinite recursion. So you get it when the method calls itself in a way that doesn't lead to reaching a base case. And the recursion continues indefinitely. It just keeps going and going. So this is what's called, leads to a situation called a stack overflow, where basically the recursive calls keep stacking on each other and you just never get a termination or a solution to your problem. In Java, this is called a stack overflow error. Okay, it's kind of similar to having an infinite loop. An infinite loop actually crashes your program. And a recursive call could crash your program, but you might also end up with a stack overflow error. It kind of just depends on a few situations that you don't have to worry about. But you could have a stack overflow error that basically becomes full and can't accommodate more function calls. Okay. In Java, each method consumes a certain amount of space. Again, you have to keep track of those local variables as you're making all of those method calls. So if the recursion is infinite and no base case stops it, you'll eventually exhaust all of the memory you have to try to accommodate that. But you just have to know infinite recursion, what it is, and how you might get it in your problem. Okay? And that brings us to the end of this lesson today. Just an introduction to recursion. There are going to be more types of problems we'll see with recursion. I just wanted to cover the basics in this lesson. So stay tuned for our next lesson where we will continue talking about these. Thank you guys so much for watching, and I will see you next time.